This is part 2 of lesson 2's notes. We were in the middle of determining the limits from this picture, and what we're going to do now is answer the 2 questions at the end and then go on to the last part of this lesson. So we are being asked to think about this. If we think of a function as a highway, as we've said earlier, then the point 2, -1 would be considered the end of the road. So let's take a look at that. So 2, -1. So if you see here at 2, -1, you wouldn't be able to go any further. You'd be at the end of the road. While the point -1, 2 is more like a pothole. So then we want to describe these 2 points. So looking at the pothole, as you see, it's the curve comes up on this side from either way. It's like you just have a little hole that you have to go around. Whereas where 2, -1 is, you can't go any further. You're traveling along the highway and you have to stop. There's a barrier. It's like having a river and crossing the river, like the bridge is out or something. Okay, so how do we want to describe the point 2, 1? So let's take a look at where that is on the graph and talk about it. Okay, so now we're here at the point 2, 1. So how would you describe that? Now, pause a second, let you think about it. Okay, so some words that come to mind are words like a barrier or another dead end. You can say end of the road again if you want. That works as well. What about the point 4, 3? Take a moment and see in terms of road nomenclature what you would consider that point. 4, 3. So that is here. Okay, I would describe that more as a bump in the road, because you can keep going, but there's definitely something you'd have to do very quickly in the car. Okay, so hopefully that street analogy gives you a kind of a visual understanding of how to look at the graph when you're talking about limits. So let's go on and do another example. So we have 3 different cases of limits that are undefined that we look at. So for this, these are all undefined limits. I forgot that word. So the first case is we have a situation like the picture there. This case is called, it's a jump discontinuity, but in calculus, what we say is that the left and right limits are not equal. So limits from the left and right are not equal or are different. Just to save a little time. They are different. Okay. It might not be a jump, but a lot of times it is for these. So we're supposed to justify why the limit does not exist. What we want to do is, so we're going to take the limit as x approaches -1 from the left of f of x, and we can just use the graph. So we're coming from the left, so we're coming in this way, and as we get to -1, we get a value of -1. And then we can take the limit as x approaches -1 from the right of the function. So this time we're coming in this way, and we get a value of +1. So what we see here is that these limits do not match. So we can say that the limit as x approaches -1 from the left of f of x is not equal to the limit as x approaches -1 from the right of f of x. So that's the justification for the first case. Now the second case is, let me make this a little bigger, what's called oscillating behavior. And we're looking at where that behavior happens. The limit exists very nicely away from zero there as you get further away. But right here in this section, we're going back and forth and back and forth and back and forth. So we have oscillating behavior. So how do we justify something like that? So what we'd say is that near x equals 0 and x equals 0.1, and of course we'd have to look on the other side of 0, x equals negative 0.1.
Custodian, come to the 1112 main office, and 1112 custodian, please report to the 1112 main office. Thank you.
Sorry, that's the problem with trying to do these at school. Okay, I'm going to keep going. So we have the limit as x approaches 0 from the right of f of x is greater, that looks terrible, is greater than 0, but the limit as x approaches 0 from the left of f of x is less than 0. So therefore, the limit does not exist. Okay, and if you were to look at values in the table for this, for sine of 1 over x, you would see that. So let me just pull that up real quick. So let's go under y equals. Put in sine, whoops, not stat, sine. So sine of 1 over x. And then if we look at our table, and I put in negative 0.1, you can see I get a positive value. If I put 0 in, it's going to be undefined. And then if I put 0.1 in, I can see that I get a negative value. So that's why we're oscillating back and forth. So if I would do the same thing, so if I put like negative 0.01 in, I have a positive value again, but if I put 0.01 in, I'm back to a negative value. So on and so forth. It oscillates back and forth. Okay, and then finally, our third case, where a limit does not exist, is where we have unbounded behavior. And what we can see is for this function, f of x equals 1 over x minus 2 squared, if we take our limit from the left as we approach 2, that is going towards infinity. And if we take the limit as x approaches 2 from the right, it is also approaching infinity. And what you want to remember is that, as I said earlier, if you want to have a limit, the limit as x approaches 2 of f of x needs to be a real number. And we don't have that case here. Neither one of our left or right limits are real numbers, so the limit does not exist. Okay, so that's how you analyze a graph. So let's look at our next one, Our next topic is talking about limits from table values. So if we consider the function f of x equals x minus 3 divided by the quadratic x squared plus 2x minus 15, we're going to complete the table as x gets close to 3. And you'll notice that I set this up, and this is a very classic way to set this up, where I take values very close to 3 from the left and very close to 3 from the right. Now I've had questions, why can't we just go to the really small values? And the reason for that is you want to make sure you don't have an oscillating behavior, that you can really see what is going on. Okay, so you're going to go ahead and put these values in your calculator as we did and check the table. I'm going to skip that step. I can do that in class if anyone needs it, but the values I got for my table are, for 0.9 is 0.1266. For 0.299 is 0.1252. For 2.999, I have 0.125. This function is undefined at 3. At 3.001, I have 0.125. At 3.01, I have I forgot to write that one down. I'll have to look it up. 0.1235. So let me just do that one real quick for you. Go to my table, and I'm just missing 3.01. I put that one in. So 0.12484. So 12484. Okay, so based on our analysis, what are the values of each of the limits? So as we come from the left, so we're coming along this way from the left, we're heading towards 0.125 or 1/8. As we're coming from the right, we're coming towards this value, which is 0.125, and again, that's 1/8. So since these two limits are equal, the limit as x approaches 3 is going to be that value, 0.125. So that's how you use a table to find a limit. So if we evaluate certain types of functions at a particular value, it may not be necessarily have a sufficient understanding of the behavior at a point. So rational functions happen because there's so many discontinuities that could come up. So that's why we have limits. And that's why I like this picture. So if you look at the picture, what we have here is we're approaching, they're building an arch support for the Hoover Dam bypass that they're, did that come out right? Hoover Dam bypass bridge that they were building. And they built it from both sides, and they're meeting here. And if you see, there's still a hole there. But you can tell by looking at that exactly where they're going to meet. And that's the idea of a limit. This bridge will only work if those two parts meet. So that's why we're always looking for a y value as we get closer and closer to a certain x value. So that leads us to our limit existence theorem, which tells us, as we've been doing, that the limit of a function at a specific point, C, exists if and only if the left-hand limit and the right-hand limit are equal. And the other important part is, not only do they have to be equal, they have to equal a real number. And that's important. They just both can't be infinity or negative infinity. They have to equal a real number. So verbally, what this is saying is the limit as x approaches c on f of x will exist if and only if the limit as x approaches c from the left is equal to the limit as x approaches c from the right. Okay, so here we go. And I want you guys to do this on your own. I'm not going to do any notes here for this. In order for the general limit to exist, the function, so please complete this little box and then we'll discuss it in class tomorrow. All right, now finally, the last example, example 7, asks us to sketch a graph to satisfy each set of conditions. What I recommend is you pause the video and try to draw one yourself. It may not match what mine is going to look like, but it should have the same kind of characteristics of discontinuities. So take a moment and do that for 7, the first box. Okay, hopefully you did pause the video. So this has 3 criteria. So the first one is that f of a is undefined. We have a discontinuity point, but the limit does exist. So that means we're looking at a hole without a jump. So I'm just going to sketch a graph here. So here's my y, my x, and I'm just going to draw a curve, and I'm going to put a little hole in it right there, like that. Okay? And so this point is going to be my A, where the hole is. So as I can see, my limit from the left is reaching that point, and my limit from the right is reaching the same point. So the limit does exist, that checked off. There is a discontinuity, I have a hole there, and I didn't put another point where f of a was defined. So that's the first one. Okay. So pause the video again and see if you can do the second one. All right, so let's try this again. So we have no limit this time, which means we could have a jump, or we could have an unbounded function. But we're told in part 2 it is a jump, and it is defined. So that means one of the endpoints of the jump has to have a closed dot. And again, hopefully your graph has the same characteristics as mine, but doesn't necessarily have to look exactly like mine. So let's see, something like I'll put my, like that. Okay, so here's my A. So the limit is not going to exist because from the left, I'm headed towards a positive value here. And from the right, my limit will be a negative value, and they're not equal to each other. So that part's satisfied. I have a jump, and since I darkened in this point right here, it's defined. Okay, I hope this helps explain how you define whether you have a limit and how graphs and tables can help you find those.